Okay, in this lecture we are going to focus on some of the details of the physical layer. For those of you who are in 475, we did not cover this in class. This particular lecture does use the book that I had everyone purchase um, in the class. So if you had 475, you probably have this book that you can follow along with. This is not from the book from this particular class. But you don't really need the book to follow along with this lecture. So we're going to cover some key points. If you happen to have read the text in the past, or you happen to read the text covers a lot of material. I wanted to focus on some of the important points. Um, there are some specifics that are not in here that I will probably get into as we talk about um, the details of communication types. Um, But for right now, we're going to focus on some of the uh, important things you need to know about the physical layer. So let's move on. So basically, what do we mean when we talk about the physical layer? So basically, gets down to what's going on in the wire or out in the airwaves. It's defining the electrical timing and interfaces by which bits are sent as signals over over a particular channel. So it's basically um, how do we turn ones and zeros into something very physical. Um, and the properties of different kinds of physical channels will determine performance. So that would include throughput, latency, and error rate, because every um, transmission medium has its own characteristics and physical limitations, and that's going to drive throughput, latency, and error rate. And data transmission rates are limited. We're going to talk a little bit about, some of the limitations that are placed on data transmission rates. Different things like signals get attenuated if they're at certain bandwidths. You have to deal with um, data losses over distances and dB losses for light 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 waves. So there's a lot of things that limit data transmission rates. Um, and we're going to basically talk about three different types of transmission media. We're going to talk about copper wire and fiber optics, basically guided media. We're going to talk a little bit about wireless, and we're going to talk about satellite communications. I did skip a few things in the book in this particular chapter that we're, like I said, we're going to get to. Um, we're going to integrate into some of our later lectures. So basically, one of the challenges in the physical layer is you have to translate analog signals into digital bits and back again. So most, whether it's light waves or electrical signals, you basically have something analog that's basically carrying digital information. And we refer to that translation as digital modulation. And the other thing that we're going to talk about a lot is how do you take multiple signals and put them on the same wire without them interfering with each other, because obviously it's very inefficient to just have a wire dedicated to a particular conversation. So we always have to support multiple signals on a particular medium. And a couple of examples of communication systems that are used in practice for wide area networks include the fixed telephone system, the mobile phone system, and the cable television system. So to be honest with you, we're really not going to cover that in this particular lecture. I will probably have I'll definitely have something on the mobile phone system when we talk about mobile communications. I didn't really feel like getting into the fixed telephone system and cable television system, except for what we've talked about so far previously, um, in a little bit of our link layer conversation, because we have so many other things I think that are more important for us to cover. So I can't cover everything, um, but keep in mind that the concepts we're going to talk about are going to be used in each of those systems. So basically, for guided transmission media, there's basically three types that are used. Twisted pair, coaxial cable, and fiber optics. So there's a lot of different types of twisted pair cable. Um, Currently want to focus on category 5 or Cat 5, as that's the most popular unshielded twisted pair. By unshielded, unlike category 6 and 7, there's not additional shielding on the wire. So the Cat 5 wire has 4 twisted pairs. The reason that the pairs are twisted is that once you twist the wires, um, it reduces the interference um, rather than if the wires were straight. If the wires were straight, you'd have a lot of noise and interference. So basically, twisting the wires results in less crosstalk and a better signal. Um, and basically, Cat 5 cable has been used for a long time. Um, when it was before we had Cat 5, you had like Cat 3 that just had like 2 twisted pairs, and originally one wire had the wires are unidirectional, but over time, technology's improved. 100 megabit per second Ethernet uses 2 pairs, one for each direction, and gigabit Ethernet uses all 4 pairs in both directions simultaneously. So our ability to do signal processing, at the network card has allowed us to continue to use, Cat 5 cable that's been used since the 10 megabit per second days, and now we can get a gigabit per second out of that same cable just by improving our signal processing capabilities. And of course, this is the standard. If you have a wired setup, this is the standard, connection for desktops and laptops that are not wireless to be connected up to an Ethernet switch. Next, we have coax cable. This is used. Coax cable was originally used in the early days of Ethernet when it was truly a bus architecture where you had literally a coax cable with T connectors going into individual hosts, and you had signal terminators at the end of the cables. Coax is used a lot today, obviously, in the cable television infrastructure. So usually from the head end, very often through a neighborhood, coax is used, or certainly used inside the home. And usually today, coax is usually 75 ohm cable, and that's usually has both your cable television intermixed with your at-home internet. We talked about that a little bit in the link layer lecture. So coaxial cable, or coax, has better shielding and greater bandwidth than unshielded twisted pair. If you look up, I typed these slides up pretty quickly. I can see I made a couple of typos here. So it can span longer distances at higher speeds. So this is why it's used a lot in the cable television business. So the old cables and the old-fashioned internet was a 50 ohm cable, which is used for digital transmission. Today, in the cable television arena, 75 ohm cable is used. And basically, from a manufacturing point of view, it basically has a copper core wire surrounded by insulating material that's encased in a cylindrical conductor with a plastic covering. And this basically, um, with all this insulation, um, it has the capability for high bandwidth and high noise immunity. You know, so with your coax cable, you don't get any, you know, any crosstalk or anything like that. So coax is going to be around for a long time, especially in the home. The next type of transmission media that's used is fiber optics. They're used mainly for long haul networks. They're also used for high speed LANs. There used to be a asynchronous transfer mode used to be a very popular, but a somewhat popular um, networking technology that was used both in wide area and local area. And certainly fiber optics are used for your 10 gig and above, you know, Ethernet switch connections. Also for your fiber to the home, like Verizon Fios, uses fiber optics. So basically, a fiber optic system has three components. It has a light source, where a pulse of light will indicate a bit. The 1 bit, I'm sorry, in the absence of light indicates a 0 bit. The medium that's being used to transmit the light, of course, is a ultra thin fiber of glass, and at the end there has to be a detector that generates an electrical pulse when the light falls on it. So if we attach a light source to one end of a fiber and a detector at the other end, we basically we can send light from the light source and convert it to electrical signals at the other end, and vice versa. And basically, to reduce light, the loss of light, we use media to refract the light back into the media. So basically, if you have the way the kind of light waves kind of work, as they traverse through different media types, there's some refraction or bending of the light waves. So basically, what you want to do is use, you know, media that you border the media send the light, so it actually refracts back into the media instead of refracting outside of the media that's actually transmitting the light. There's basically two types of fiber that is used, and basically what drives it is the type of wavelengths of the lights. So multimode fiber sends out light with longer wavelengths and uses multiple light rays that bounce at different angles, but all of them stay within the media. So because it's multiple light rays at different angles, the lights have different modes. So we refer to that as multimode fiber. I didn't write down here, but I believe it's like, I think it's like 10 kilometers, I think is the, or maybe close to 2 kilometers is the limit for multimode fiber. I used to manage a network that went across our campus, and that was one of our challenges. Because multimode fiber is a lot cheaper than single mode fiber, but one of our challenges was going from building to building, which fiber we had to use. So I imagine if it was on campus, I think 2 kilometers is probably the limit for multimode fiber. Single mode fiber is used basically for more long haul connections. Basically, that's what you're going to use for your cables that get laid along the ocean bed. Basically, long haul fiber uses whose distances okay, so I think what I wanted to say, a little typo here, but I think what we're trying to say is that the light sent on a single mode fiber, um, because it uses light that has very small wavelengths. So basically this causes the light to travel in a straight line without bouncing. And it's basically because of that, you have a lower dB loss, so you can transmit data on that light wavelength for a longer distance, basically up to 100 kilometers, without any amplification. So one of the issues with transmitting light is that you have a little bit of dB loss over time, and basically it's not actually dB loss is not linear to wavelength, as you can see. So different wavelengths have different attenuation properties. So basically there's three common wavelengths used for optical communication. 0.85 microns, 1.3 microns, and 1.55 microns. So 0.85, even though it has, this should say has higher attenuation. Okay, it has higher attenuation than the other wavelengths, as you can see. So there's two little, those little bathtubs here that at 1.3 and 1.55 microns, their attenuation is very good. But 0.85 is used because basically the type of material that you would use to create the lasers and electronics can be made of the same material, so you can. It's very easy to manufacture the components to send light at 0.85 microns. So it makes it a cheap way to transmit a light signal. So basically you kind of use this for your shorter lengths. And 1.3 and 1.55 are used for your longer distance lengths. So how are fiber cables manufactured? So you have a glass core at the center. It's obviously a little bit bigger for multi-mode fiber at 50 microns. Single mode fiber is 8 to 10 microns, so that's why you have the light signals that don't have very high amplitude because of the glass core is so small. The core is surrounded by glass cladding with a lower index of refraction, so this way the light refracts, and it's set up to have the type of cladding and have properties so that the light refracts inside of the glass core. Around the cladding you have a plastic jacket, and usually fibers are grouped into bundles that's protected by an outer sheath. So you see in this particular example, there's 3 fibers bundled in this particular example. Basically, there are 2 different types of light sources used for fiber optic cables. You can use LEDs, which are cheaper, and semiconductor lasers, which are more expensive. LEDs support a lower data rate because they're more susceptible to, it's not as strong of a signal, more susceptible to dB loss. Whereas semiconductor lasers can support a higher data rate. LEDs are limited to the shorter run multi-mode fiber Semiconductor lasers can be used for for either a multi-mode or a single mode. LEDs are limited to short distances, with semiconductor lasers are used for long distances. Um, the good thing about LEDs is they have a lot longer life than semiconductor lasers. Um, they are also not as affected by temperature sensitivity as semiconductor lasers, and of course they are less expensive. So those are trade-offs between the two. So obviously you have to look at what your application is, what type of network you're designing, and you got to let these factors come into play. Obviously, using a long haul network where you can, you'll have to kind of protect your lasers from temperature changes. But if you're anything long haul, you're pretty much limited to using semiconductor lasers. Where if you're doing something on a campus or a closer by network, or at the local end, you can use LEDs as your light source. Okay, next we want to talk a little bit about electromagnetic waves. So we're going to kind of focus next on um, how basically on copper wire and sending signals through the air and the electromagnetic properties.